area name. That area will be a code memory and it is a read-only memory. We will define a area. We'll give a area name as factorial, fact. Then this area is written with a code that is a read-only memory. Next, here in this program, we are going to find the factorial of a number. The factorial will take number, for example 5. We need to find factorial of a number 5. It is like 5 into 4 into 3 into 2 into 1. It will be 120. It is equivalent to 78 in hexadecimal number. The same if you verify in the calculator, 5 into 4 into 3 into 2 into 1 is 120 in decimal, and it is equivalent to 78 in hexadecimal number. To write this program, first we need to define a register which is having this number. We'll use this R0 to save our number which we want to find the factorial. R0 will be 5. Next, we will initialize the result register where we will save the result. We'll initialize R1 as our result register. In R1, we will save our number 1. Next, we will compare this factorial number with 0. Here we will write the instruction call as compare R0, #0. It will compare R0 and 0. Now we have R0 value as 5. 5 is not equal to 0. Then that 0 flag will be 0. In comparison, it will check this flag register. Here we will check for 0 flag register and it will be 0. Because this R0 is not equal to 0. Next, if it is 0, it will stop the program. If we are finding the value, the factorial value for 0, we will stop it at the beginning itself because factorial of 0 will be 0. Here to check that, we will write an instruction. We'll have a label stop. Here it is not 0, it will not stop. If it is 0, it will stop. 5 will be 1 and comparison value R0 will be 0. So that's why it will stop. If it is stop, it will go to the label stop, and at stop we have written a no op instruction which does not do anything and will end the program. Now it is not equal to 0. We'll continue program. We'll copy the same number to one more register, that is a register R1. Now in both the register R0 and R1 we have a value of 5. We will decrement that number. We'll decrement that number is in R0, let 1, that will become 4. We have done this because we need to multiply this 2, 5, 2, 3, 4 and 5. To multiply first, before multiplication we will compare this with 0. If it was 1 and 0, we'll get the value. We need to compare it with 0. If it is 0, we will come out of the loop. We will not multiply. To write that, we have a compare instruction. We will compare R0 with 0. If it is not 0, that is 0 flag will be 0 and it will not jump. To check that, we have an instruction branch if equal. If it is equal, that is if the value of R0 is 0, it will stop. If it is not 0, in this case it is not 0, it is 4. It won't jump to stop. It will continue the next instruction. We will multiply these values R1 and R0. That is 5 into 4 and the result we have stored in R2. 5 into 4 is 20, which is equal to 14 in hexadecimal value. This will save in our result register, that is R1. In R1, we will copy the value from R2, that is we have 20, that is equal to 14 in hexadecimal. We'll copy it to R1. Next, we need to do the next number, we need to multiply, that is 20 is multiplied with 3. We will branch to the next instruction, that is we will check from the subtract. We'll go to the subtract instruction, that is we had in R1. R0 is 4, R2 is 1, 4. Now that is subtract R0 comma 1. It was 4, now it will be 3. We'll compare with that with this number is 0. No, it is not equal to 0. We'll jump to the next instruction, that is it will multiply R1 and R0. That is R1 we had for 20, that is 14 in hexadecimal. Now R0 value is 3. So that 20 into 3, that is 60, 3C in hexadecimal number. We'll copy the result into our resultant register R1 using move R1, R2 instruction. Next, again we will continue with the same loop. In this loop, we'll reduce by decrementing this R0 value, that is from 3. Now it will be 2. Again it will check for R0 value whether it is 0 or not. If it is not 0, it will continue with the instruction. If it is 0, it stop the execution. So if it is not equal to 0, it won't jump to the stop label. It will continue with the multiplication. Now it will multiply R1 into R0, that is R1 is 60 into 2, that is 60 into 2 is 120. We'll copy that same number in the result register, that is R1. Next we'll jump to the next again label. In this loop we'll reduce decrement R0 value, that is from 2 to 1. Now we will compare the value again R0 with 0, that is not equal to 0, it is 1. It will not jump to the stop instruction, it will continue the multiplication instruction. We will multiply R1 into R0. R1 was 120, now R0 is 1, 120 into 1, 120. We'll have 120 itself, the value equivalent to 718 hexadecimal. We'll move it to our result register R1. Next again it will branch to next instruction B, next. It will branch to the again next instruction in this loop. We will reduce the value of R0 so that from R0 it was 1 and now it will become 0. We'll compare this R0 value with 0. Now R0 value is 0. That's why we have 0 flag is equal to 1. Once this 0 flag is set to 1, we will check this branch is equal. Yes, it is equal. It will jump to the stop instruction. It won't do any multiplication. It will jump to the stop instruction. That is, we have no op instruction at that stop label and we will end the program using the directive. Finally, at the result register R1, we have a value 120, that is 78 in hexadecimal. Now, the same program is written in Keel Microvision. We'll execute the program. We'll open this Keel Microvision. We'll create a new project. We'll go to project menu, click on new Microvision project. It will show a result. You will give a name for this project. Give the name fact. We'll save that. So we should know where we are saving this. So as we have created a folder by name ABC, we'll save the Factorial program project in the same folder. Next we need our target. Target is LPC2148. So if this is LPC2148, click on OK. It will ask for start. So don't need to start. We can observe here it has created a target file. In the target file we have a source group. Now we'll open a blank file. We'll click on new. It will create a blank file in this project. We'll save this blank file. We'll save this blank file in the same folder where we have created. So we'll give the name fact.asm as we are writing the program in assembly language. We need to give the extension as .asm. We'll save this. Now we can observe that our file is fact.asm. We need to add our file to our source group. We'll right click on source group, click on add existing file. We need to select our fact.asm. We need to select here source file. Now we can see that fact.asm. Click on that, click add. We close that. We can see here fact.asm has been added over source group. Now we'll write the program. Once we write the program, we need to see that this directives and instructions should be written after a tab. They accept these labels. We have a label start, next and stop. These labels should be written without any of the tab. Other instructions and directives should be written after a tab. Once we have written the program, we'll save this program and we'll debug. We can't see our debug window. To see that, we need to go to window, reset windows to default so that we can see our build output window. We'll debug this or click on this build a file. We'll click on this build. We don't have any errors or warnings. If you have any errors, we'll get here. You have one error to add up like that. We can debug that. We can again that we build the program. Now we don't have any errors or warnings. We'll continue. We'll click on this start or stop the work session to debug this program. Click OK. It will open the debug window. In this debug window, we can see we have different windows. We have a register window. We'll drag this. We can look all the values of our register. Now the pointer is pointing to the first instruction. There is R0 which has 5. That will keep our factorial number in our register R0. We'll execute this program step by step. We'll click on the step icon. That one instruction is executed, that is move R0, 5, value of 5 is moved to R0. Next we will move this 1 to our R1 register so that it has moved 1. Now we will compare this value R0 with 0. It is not 0 so that it won't jump to stop. We can see that 0 flag is not 1, that is 0. That's why it won't jump to the stop instruction, stop label. It will continue with the next instruction. Now R1 will get the same value as R0, that is 5. We can see that we got this value 5. In the next instruction, we'll subtract the value of R0. R0 as 5. Now it will be 4. We'll compare this value R0 with 0, whether it is 0 or not. If it is 0, we'll stop the program. So it is not 0, it will continue. So flag is not 1, it is 0. It will continue. That is 5 into 4. Now it is 20, that is 14. 14 is the hexadecimal value. Next 25 into 4 is 20, that is 14 and is equivalent to hexadecimal value. Now we will save that result 14 in the result register R1. Jump to the next label, that is subtract R0 to 1. So R0 value is 4. It was 4, now it will be 3. Now we'll check whether this value is 0 or not. It is not 0. Next 14 into 3 in hexadecimal, that will be 3C. Next again we'll jump to the next label instruction. We'll subtract the value of R0, that will be 2. We'll compare whether this value R0 is 0 or not. It is not. It will go for multiplication. We will multiply 3C into 2. So that is 120 is equivalent to 78 in hexadecimal. Now we'll again go for that same loop. We'll decrement the value of R0. Now it will become 1. this is not equal to 0, it will continue, it will multiply. In multiplication, 78 into 1, it will be 78 itself. We'll move the same value to result register R1. We'll decrement the value of R0, it will be 0. Now it is 0, it will stop. We can see 0 flag is set to 1. It will come out of that blue and it will go to the stop instruction. It has been stopped. The result value 78 in the result register R1. So we have verified that our factorial of 5 is 78 in hexadecimal. That is 120 in decimal value. So we'll stop the debug. If you want to change any value, we need to stop the debug session and we can change here any value and we will set the new values and we can verify with the other values. So in this program, we have seen how to write the factorial program for ARM7 using the Keil microvision.